Hi, today we're going to be talking about section 11.4 in Stewart, which is about the comparison tests. So to motivate the comparison test, we're going to recall the monotone bounded sequence theorem. This was a theorem about sequences that always move in one direction, but they have a bound that stops them from going too far. So those sequences are going to be convergent. Okay. In formal terms, if Cn is a monotone increasing, obviously the same could be said for decreasing, but we're using increasing, and bounded sequence then Cn converges to a limit L. Okay. And we don't know, the bound is not necessarily the limit. The limit might be below the upper bound that we know about, but it's got to be somewhere at that bound or below. Okay, so let's apply that to series. Suppose that we have two series, AN and BN, and these are series with positive terms. We're going to explore two situations. The first situation is that the series Bn is convergent, and An is less than Bn for all n. Okay, so all of the terms of the A series are smaller than the terms of the B series. Okay, in these circumstances, the series AN also converges. Why is this the case? How do we know that this converges? Well, we can use the monotone bounded sequence theorem. Okay, so we know that, so let's take the sequence of partial sums. Partial sum Sn equals sum from k equals 1 to n of ak. We know that this is a monotone increasing sequence because all of the terms of the series are positive. So this is monotone increasing. And we also know that it's bounded above by the limit of the partial sums of Bn. Okay? For that reason, by the monotone bounded sequence theorem, the sequence of partial sums converges, and that means the series is convergent. By the monotone bounded sequence theorem. Okay, what's the second case? If the sum of Bn diverges and an is greater than bn for all n, so you have this series where the terms are getting you up to infinity, and then you have a larger series than that, the term-wise larger, then that other series also diverges. Okay. Why is this true? Well, again, we'll look at partial sums. So if we take Sn equals the sum from k equals 1 to n of ak, we know term by term this is going to be bigger than the sum of the bk. Okay, and when you have positive terms and each one is greater than its corresponding term in the B series, then the sum is also going to be greater. Let's call this Tn. Then the fact that the limit as n goes to infinity of Tn equals infinity implies that the limit for Sn is also diverging to infinity. Okay, so using these two facts, that Bn converges implies An converges, and Bn diverges implies An diverges, well, should be careful. Bn converges and An less than Bn, then the series An converges as well. Series Bn diverges and An is greater than Bn, An diverges as well. This is called the comparison test. So, this is the comparison test. Okay. So for a series A sub n that you're looking at and you want to test for convergence or divergence, find a convergent series sum of Bn so that An is less than Bn, or find a divergent series series of B sub n so that A sub n is greater than B sub n for all n. Okay, that's what the comparison test is all about. Looking for that right series that we can compare to decide if our series of interest is convergent or divergent. We're usually going to focus on P series and geometric series. These are the series we know most about, and they're usually pretty useful for comparing to most things. So remember that P series, this is a series of the type sum of 1 over n to the p, and this is for p greater than 1, this is convergent, and for p less than or equal to 1, this is divergent. Geometric series are series of the form ar to the n minus 1. I should add the indices here so it's not confusing. And this is for r less than 1, I should say absolute value of r less 1, or r between minus 1 and 1, this is convergent, and otherwise it's divergent. Okay, and these are the standard series that we're going to try and compare to. Not universally the case, but in most examples. Okay, so let's take a look at an example. Consider the series sum as n equals 1 to infinity of 1 over n cubed plus 3n plus 1. Okay, looking at this series, it looks a little bit like a p-series. We've got a power of n in the denominator, but it's not quite a p-series because we have these other terms. So how can we react to it? So we're going to try to compare to 1 over n cubed. Okay, well, n cubed plus 3n plus 1 is greater than n cubed for all positive n, because we're just adding positive stuff here. Okay, so that means that 1 over n cubed plus 3n plus 1 is less than 1 over n cubed for all n greater than or equal to 1. And this is what we need for the comparison test, because 1 over n cubed is a convergent p-series, and 1 over n cubed plus 3n plus 1 is less than 1 over n cubed for all n in the range that we care about. Our series converges by the comparison test. It was pretty clear what we should compare the series to, but and it was quite easy to do the comparison, but let's make it a little trickier. Let's consider the following example. Okay, let's consider the series, very similar one, but slightly different, 1 over n cubed minus 3n plus 1. Go from n equals 1 to infinity. Okay, this looks similar to the last one. We would naturally try the series 1 over n cubed for comparison. But n cubed minus 3n plus 1 and n cubed, this relationship is a little bit uncertain. For instance, when I take n equals 1, so let's draw this out. N equals 1. I'll put n cubed here and n cubed minus 3n plus 1 here. N equals 1, n cubed is 1, n cubed minus 3n plus 1 is minus 1. When n is 2, n cubed is 8. N cubed minus 3n plus 1 is 9 minus 6, or 3. And when n equals 3, n cubed is 27. N cubed minus 3n plus 1 is 28 minus 9, or 19. Okay, so it looks like n cubed is larger than n cubed minus 3n plus 1. So probably something like that. But if n cubed is the larger thing, then when we take the reciprocal, we're not going to have the comparison that we're looking for. So what can we do? How can we resolve this situation? Well, we can look for another series that we know converges. We have a hunch that this behaves like 1 over n cubed, so we expect it to converge. We just need something that we can validly compare it to. So let's use instead a different p-series. Let's try 1 over n squared. Okay? So now we can add in a row to this graph, n squared. At n equals 1, we have 1. N equals 2, we have 4. N equals 3, we have 8. Let's add another column here. When n equals 4, n cubed is 64. N cubed minus 3n plus 1 is 53. And n squared is 16. So after n equals 2, n squared is less than n cubed minus 3n plus 1. Okay? Which means that 1 over n squared is greater than 1 over n cubed minus 3n plus 1. And we know that 1 over n squared is a convergent series, and if you have a comparison where your series is smaller than the terms of a convergent series, you know it converges. Because 1 over n squared is a convergent p-series. Our series of interest also converges. Okay? Let's look at another example where it's not just algebraic expressions. Let's switch up our colors, why not? Consider the sum from n equals 1 to infinity of ln of n over n. Let's look at the first few terms of this. So when we have n equals 1, log of 1 is obviously 0. So that's our first term. Log of 2 over 2, we can just put that in on its own. Log of 3 over 3, etc. What do we think about this? Well, if I were to ignore the logs, it looks like the harmonic series, 1 over 2 plus 1 over 3 plus 1 over 4, etc. But the logs actually just make it bigger. It doesn't make it smaller. We know the harmonic series diverges, and these logs are just making it bigger. So why don't we do comparison to the harmonic series? Okay, so after you ignore the first term, and you can ignore any finite number of terms, because all we really care about is after a certain point, it's always true for all of the infinitely many terms after whatever point. So maybe it's not true for the first million terms, but after that it's true, then that's fine. So for n greater than 1, actually let's make it n greater than 2, because I think e is between 2 and 3. So for n greater than 2, ln of n is greater than 1. And that implies that ln of n over n is greater than 1 over n. The sum of 1 over n is a divergent p-series. So our sum, ln n over n, diverges by the comparison test. So we had a bunch of examples there where it was a little tricky to find the exact right series to compare to. And there's a theorem that helps us with this. It's called limit comparison theorem. And instead of saying that you have to be precisely less than or you have to be precisely greater than, it's saying if the ratio converges to some non-zero finite number, then those two series will have the same behavior. Okay, so just in terms of the examples we just did, so looking at the series 1 over n cubed minus 3n plus 1, we have an intuition that it should behave like the series 1 over n cubed, even though ultimately that wasn't the series we ended up comparing it to, but that was the series that we think it should act like. So the limit comparison theorem is as follows. If you have two series, an and bn, sum of an and sum of bn, and they're series with positive terms, if the limit as n goes to infinity of an over bn equals c, where c is greater than 0 and is finite, then one of the two of the following things has to hold. Either both series converge, or both series diverge. Okay. So, looking back at that same example with 1 over n cubed minus 3n plus 1, so take the limit as n goes to infinity of 1 over n cubed divided by 1 over n cubed minus 3n plus 1. And we find this is, we can simplify fractions. Limit as n goes to infinity of n cubed minus 3n plus 1 divided by n cubed distributing, we can get limit as n goes to infinity of 1 minus 3 over n squared plus 1 over n cubed, which is 1. And this is a finite number greater than 0. So by the limit comparison test, both series either converge or diverge. But we know that the series 1 over n cubed converges because it's a p-series, it's a convergent p-series. So that implies our series also converges. Let's do another example. Consider the sum from n equals 1 to infinity of 6 to the n divided by 5 to the n minus 1. Now we're looking at the series 6 to the n divided by 5 to the n minus 1. So this looks like a geometric series. We have powers of n. And if we were to ignore this minus 1, it would just be 6 to the n over 5 to the n. This looks like the series 6 to the n over 5 to the n, which is also 6/5 to the n, which we know is a divergent geometric series. But we have to deal with this 5 to the n minus 1, so we could try and make the comparison test work, but we could also use the limit comparison test. So let's apply the limit comparison test. Let's take the limit as n goes to infinity of 6 to the n divided by 5 to the n minus 1 divided by 6 to the n divided by 5 to the n. Simplifying fractions, this is limit as n goes to infinity of, well, it's 6 to the n, 5 to the n, divided by 6 to the n, 5 to the n minus 1. And that's the limit. Well, we can cancel out the 6 to the n's. And if we cancel out the 5 to the n's as well, what we're left with is 1 divided by 1 minus 1 over 5 to the n. Clearly, this term is going to 0. So this limit is 1. Okay? And that's exactly what we want from the limit comparison test. It's a finite number. It's greater than 0. So this means that both series, in this case, diverge because it's a divergent geometric series. Okay. Another type of question you might run across is algebraic expressions that involve roots. So for example, square roots of polynomials or cubic roots of polynomials. Let's do one like that. So let's say we have the sum k equals 1 to infinity of cube root of k divided by square root of k cubed plus 4k plus 3. Okay? So the trick that I want to suggest that you use here is to just look at the biggest parts of every expression. So just focusing on the largest part, this would be the sum from k equals 1 to infinity of cube root of k divided by square root of, and I'm going to ignore the last two terms and just take square root of k cubed. Okay? Well, I could turn that into the sum of k to the 1/3 divided by k to the 3/2. Okay? And when you have an expression like that, you can subtract the exponents, and what you'll end up with is the sum of 1 over k to the 7/6. Okay? And that's the series that I expect I'll be doing the limit comparison test with, because that's what the biggest parts of the series indicate the behavior will be. So let's do limit comparison test. Limit as n goes to infinity of, okay, the term of one series divided by the terms of the other series. So it's cube root of k divided by square root of k cubed plus 4k plus 3 divided by 1 over k to the 7/6. And this is equal to limit as n goes to infinity of k to the 7/6 times cube root of k divided by the square root of k cubed plus 4k plus 3. Okay. And what I'm going to do now is I'm going to factor out the k cubed from this square root. Okay, so now I'm going to have on the top, so first let's get the limit written out. Oh, this should all be k's, excuse me. So k to the 7/6 times cube root of k divided by, okay, now I'm factoring out the k cubed, so it'll become k to the 3/2 because there's a square root, times the square root of 1 plus 4 over k squared plus 3 over k cubed. Okay. So when I have k to the 7/6 times cube root of k, adding those exponents together, I'll get k to the 3/2. So this is really equal to the limit as k goes to infinity of 1 over the square root of 1 plus 4 over k squared plus 3 over k cubed. And that's by combining these exponents, then canceling with this. And this is clearly 1 because these terms both go to 0. Okay, 1, once again, is a finite number greater than 0. So both series either converge or diverge. Since 1 over k to the 7/6 is a convergent p-series because 7/6 is greater than 1, then our series of interest, cube root of k divided by square root of k cubed plus 4k plus 3, also converges. Okay? Okay, I'm going to close with quite a tricky one, because these problems can get quite tricky, but if you keep your head and you think about what you might be able to compare to, what series you're familiar with, anchor yourself at the series that you do know how to deal with, then you'll be able to deal even with the more difficult ones. So let's finish off with that. Okay, this next example, just make sure the camera's adjusted. This next example is the sum from n equals 1 to infinity of n factorial over n to the nth power. Okay, that is an unusual looking series for us. We probably have to mention that n factorial, which is written as just n with an exclamation point, it's the same thing as 1 times 2 times 3 up to n. Okay, you're listing all of the integers and multiplying them all together up to your value n. Okay, so let's write out the first few terms here. Okay, so we'd start with n equals 1, so that's 1 over 1 to the 1, which is just 1. And then we would have 2 factorial over 2 to the 2, so let's write this out fully factored. Okay, the next one is 3 factorial divided by 3 to the 3. 1, 2, 3 over 3 times 3 times 3. Okay, then another expression is 1 times 2 times 3 times 4 divided by 4 times 4 times 4 times 4. Okay, so looking at this series, it doesn't look like a geometric series, really. It doesn't look like a p-series. But what we might notice is that we have, in each term, we can kind of group things like this. We have a quarter times 2 quarters times 3 quarters times 4 quarters. Okay? And what we'll notice, all of the factors are less than 1, less than or equal to 1. Okay, so if we can isolate some part of it that's small, and then just multiply by these other small numbers, so it only gets smaller, we'll be able to compare to something that is similarly, that is convergent. Okay, it'll be smaller than something convergent. So my archetypal convergent series is 1 over n squared. Okay, so if we look at, and instead of 1 over n squared, I'm going to use 2 over n squared. And what we'll notice is n factorial divided by n to the n is less than 2 over n squared. Why is that the case? Well, this is equal to 1 over n times 2 over n times 3 over n up to n over n. Okay? So this part is equal to 2 over n squared. Okay, so maybe let's make this less than or equal to, even though generally it is less than. This part is less than or equal to 1. Okay? So that means that the product will be less than or equal to 2 over n squared. But we know that the sum of 2 over n squared, that's just equal to twice the sum of 1 over n squared. Which is convergent, as we know, is a convergent p-series. So by the comparison test, our series n factorial over n to the n also converges. So sometimes you have to be a little creative looking for a series to compare to, but you know, trial and error is often the best way to do it. Think about trying out a few terms, seeing what is this less than, what is this greater than. Can I anchor it to something that I'm more familiar with in terms of p-series or geometric series? Okay, and I think we'll end it there. Thank you.